And it's on. So, hi everyone. We have two guest speakers today. Andrei will talk about symbolic execution and Raoul about formal verification. And we'll see how we apply these techniques or processes to increase smart contract security, right? Because that's what we're interested in. So, and then they will talk about tools that they work on for developers and auditors. Okay, so Andrei, when you're ready.
I actually think that Raoul, do you want to start first?
Okay, whichever.
Yeah, I'm going to start.
Go ahead.
So I'm sharing my screen. Let me all know when you can see it. All right, can you see my presentation?
Yes.
Okay, so welcome everybody. I'm Raoul from Runtime Verification, and here with my colleague Andrei. I'm working on Symbolic, this new tool, which is kind of a hybrid between a symbolic execution engine and a Solidity debugger. And Andrei is working on Control, which is well, a symbolic testing and formal verification tool. But they are both built on the same underlying engine. So it makes sense to present them together. And the order in which we go is I start first with the symbolic debugger because it's it's more intuitive. And then Andrei will take over for the second half of this meeting, and he will introduce like control, and he will go into a bit more detail than I do. So before well, I can tell you all day long how cool Symbolic is, but you can actually try and go convince yourself. It's we have a free online version, so you go to trysymbolicruntimeverification.com or just follow this QR code, and it will load a Visual Studio Code instance in your browser with Symbolic installed, and you can just start debugging a function by just clicking this small debug button that we show both all public and external functions. And we will have a demo also in this session. So it can be a bit, you need some getting used to it, but let's start with a little bit of background theory and where this is all coming from. So I'm pretty sure you have not used a symbolic execution debugger before because, well, at this stage, symbolic execution debuggers have been only the domain of academics and research papers. But as far as I know, there's no like industrial ready symbolic execution debugger. And so Symbolic is probably the first one, and it's for Solidity. On a very basic level, it's the marriage between two techniques. The first one is debugging, where you can just set breakpoints, inspect variables, see what's on the call stack. And the second one is symbolic execution. Symbolic execution is a systematic way of exploring your program state and digging into all the different, like really all possible edge cases. And I will make this clearer in this presentation. So I assume that you are somewhat familiar with debugging, but I don't assume that you have any prior knowledge to symbolic execution. So we will start from first principles. And when you Google symbolic execution, well, you will find a lot of research papers because that's where it's coming from. And that can be scary. And sometimes these papers are super hard to read. But if you take one thing away from this presentation, it is trust your intuition when it comes to symbolic execution, because you already are a skilled symbolic execution engine. Like really, when you're reading code, you're doing it symbolically. And here's one example that I laid out in front of you. So we have this small program that is checking if we have, like, if our balance is at least something, and if not, it will revert. And if we have enough balance, it will make a transfer. So this could be, this code snippet on the top left corner could be a snippet from a transfer function, for example, from an ERC20 token. So, and when I ask you to read this code and tell me what you think this piece of code is doing, what you do internally, like mentally, is you start symboling it executely. You start executing it symbolically in your head. What that means is, for example, I tell you, hey, we have an initial state, the value, the from, and the two variables. I'm not going to tell you what these values actually map to. I just say, hey, these could be anything. And then I have some other variables like this balance of and of the from address, like the initial balances of the users. And I can say you, hey, these are concrete numbers. So we start with an initial balance of 100 for the sender and with an initial balance of 200 for the receiver. So the lesson here is symbolic execution does not mean or does not imply that everything in your initial state needs to be symbolic. You can have some symbolic variables and you can have some concrete values, and mixing them is perfectly fine to do. So then I ask you, well, step over this from this initial state, execute over this if statement. And the first thing that you will note is, well, you cannot really know at this point if this if condition is evaluating to true or to false. And that is because, well, you do not have sufficient information. I never tell you what is the concrete value of this value variable, right? So you need to consider both branches. Like you need to see what's going on in the then branch, and you need to see what's going on in the else branch. So let's first look at the else branch, or let's start with the then branch. That's the logical order, right? So the left branch on this slide. And when we enter this then branch, we gained some additional knowledge, right? Because we know that the value must be bigger than 100. We learned this from the if condition. If this was not the case, we would not be in this branch. So while we are symbolically exploring the branches, we actually learn more about our state. So, and in this state, we have what we call an additional path condition or path constraint recorded that tells us, hey, value is bigger than 100. And in this state, well, in this then branch, there's only one statement left to execute. That is a revert statement. So we're going to revert. And then we are done. We are terminated. So, but now we still have to look at the other branch, right? We still have to look at the else branch. And again, as soon as we enter the else branch, we learned some additional knowledge. We now know that, well, value is at most 100. Again, otherwise we would not be in this branch. So, and then we can execute over the balance assignments, do the internal accounting. And what I did here, like really, really slowly, I bet like when you're reading this code on the top left corner, you do this within some seconds. Like your thought process is so well suited to symbolic execution. You do it automatically within seconds. But for the purpose of this presentation, I want to show you a little bit the background theory. So I wanted to do it once very slowly for you. So just trust your intuition when it comes to symbolic execution. So, but, well, let's motivate first why this is at all needed. And let me build kind of the motivation for symbolic execution and the symbolic debugger. So you might have heard somebody say that the EVM is a state machine. And what that means is, well, we had some initial state. Back in 2015, the first Ethereum, the Genesis block was mined. That is our initial state. And then users started putting transactions on the network. The network recorded these transactions, and every transaction makes a state change, right? It takes the EVM state from a state before the transaction to a state after the transaction. So for example, if I'm going to send a transaction and transfer 100 USDT to Andrei, then before my balance would probably be 100. And after I transferred, my balance would be 0 and Andrei's balance would have increased. So that's the states that changes with every transaction. So let's zoom out a little bit from one singular transaction and lay it out on the timeline. So we have here 2 axes, and on the x-axis you see, you see time lined out, and on the y-axis you see space. Let's start with time because that's simpler. So in 2015, we had this initial state mined. Then we recorded a bunch of transactions. And somehow we ended up in the present, right? And here we are. We can look at the past and we see, well, we have recorded some million transactions for Ethereum. They all changed the state, and here we are with our current state. And we know that some of these states in the past have been bad states and they have been exploited, right? And we can be sure that in the future, like, there will also be bad states and they are also going to be exploited. And that's bad, right? From a security perspective, people are going to lose money and people lose their jobs. So we need to kind of find all these bugs in our future transactions. Now, the problem is really, it's even hard to do that for the past. Like, if you look at some of the exploit transaction sequences, these exploits, they are becoming more and more complex. Now imagine doing that for the future, like where you cannot predict the next transaction. So there's an infinite amount of possible next transactions that could come in. It could be someone doing an ERC20 transfer. It can be someone trading on Uniswap. It could be someone staking tokens. We can't know. And even if we could predict just the next transaction, the game would repeat itself, right? And now we have an infinite possibility of next states. And from there, there's another infinite possibility of next states. So that's what we call like the state space explosion problem. And that's what we see on the vertical axis, like the future is branching out into zillions of possible futures, and some of these possible futures contain bugs, and we need to somehow figure out where these bugs are now before we deploy our smart contracts, and that's where symbolic execution comes in. So how do we solve this problem with symbolic? So first of all, what we do is, well, we try to collapse the possibilities, the state space into abstract states. So instead of, for example, here on the top of the slide, you have 3 concrete transactions where Alice transfers first 10 tokens to Bob, or she transfers 20 tokens to Bob, or Alice transfers 30 tokens to herself. And all these different transactions, they lead to different post states that you can hear on the right-hand side. So in the first state, Alice has 19 tokens after the transaction. In the second state, Alice has 80 tokens, and so forth. So what we do in symbolic is, instead of like considering all these possibilities individually, where Alice tries to like transfer different amounts of tokens, we collapse them into an abstract transaction. And abstract here means that some of the parameters of your transaction can be are not determined. They are not fixed to concrete values. For example, here, this abstract transaction, the yellow one on the bottom of the slide, it has a fully symbolic from address and a fully symbolic to address. And even the value that we are going to transfer is not known. So this is how we collapse space, like from an infinite possibility of transactions into a single abstract transaction. So that leaves us with the problem of time, right? And the problem with time is a little bit more nuanced, and it's harder to diagram it, but the cool thing here is, like, with these abstract transactions, we actually don't care about when our transaction is applied in the future and in which alternative future it is applied. So again, on this slide, you have one concrete transaction in gray, and then you have one abstract transaction in yellow. And you can see like the starting state of the initial of the concrete transaction at the top, where Alice has a balance of 80 and Bob has a balance of 20, that this state is subsumed into the abstract state below it, the yellow state, right? So if we assign $from to Alice, $to to Bob, $x to 80, and $y to Bob, then we arrive at this concrete state. So that is what we mean by the abstract state is more general, is more general than the concrete state. So, and now the trick here is that we play, well, you can also see that the final state of the transaction, where Alice has a balance of 60 and Bob has a balance of 40, that's also subsumed in the initial state of the abstract transaction. If you follow this arrow, this dotted arrow at the right that goes from the gray box to the orange box, and then follow this arrow again that goes from the final orange state to the initial orange state, you can see by transitivity, we call that probably transitivity, but that's, forget how it's called, but by just following the arrows, you can see that the final state is also subsumed in our initial state. And that means that we can apply this abstract transaction to any alternative timeline in the future. And if this is too abstract, well, I have one more abstract diagram on this, and then we are going to go into the demo. So ultimately, that means what we did is, so we started with this problem where you have infinite amount of possibilities, alternative timelines, some of them are buggy, and we must find the bug. So what we did is we reduced this problem to, well, a simpler problem that is just, we have one abstract transaction that we need to consider, and we need to see, hey, is there any execution path in this abstract transaction that could be buggy? And notice I'm saying, well, this problem is maybe simpler than exploring an infinite amount of possibilities, but it's definitely not easy to do. It still takes some skill. But that's where our tool comes in, and hopefully it makes debugging these abstract transactions easier for everyone. Okay, I'm going to skip this slide because I think we don't have the time. I also wanted to do the demo. This is a sneak peek. I think I can also skip this slide because, well, you will see it live in action. So I don't need to talk about a screenshot here. Time travel debugging is a nice thing. So I talked a lot about like time and space. And well, when you are dealing with alternative timelines, and that is what symbolic execution actually does, it considers all possible futures, then it can, well, you can get lost. Like if you have watched a time traveling movie, it's easy to lose the red thread, right? And lose orientation. The same is true for debugging symbolic transactions. So therefore, we have this nice time travel debugging feature where you can actually, instead of just stepping over one statement at a time, you can also go back, like step backwards in time. And even better, you can also directly jump to alternative timelines. So that's why on this slide, you have this graph on the right that basically visualizes all the possible timelines, and you can just select one node to jump to this specific point in time in this specific timeline. Okay, let me, I think it's demo time. So let's use this demo that you can also access on your browser, go to try-symbolic-runtimeverification.com so you can play along. You can also do that after our call. So this demo is very limited in scope. You cannot upload your own source code there. You can only debug the wrapped ETH contract. So wrapped ETH, for those who don't know, it's a famous contract that wraps the native cryptocurrency of Ethereum, which is called ETH, into an ERC20 token. And ERC20 is the standard that is used for all the non-native currencies or tokens, whatever, of a blockchain. So you have this contract, and you have all the classical functions that you would expect from an ERC20. You have a proof, transfer form, deposit, and maybe let's just start with a simple function that's also kind of interesting. So I want to start with let's start with the withdraw function. So, and in order to start debugging it symbolically, all I have to do is click this debug button. And then it automatically stops at the first line. So, and notice I clicked this debug button, but I never specified what is the value that I want to transfer, to withdraw. I left that open. And symbolic execution means that we just treat this parameter as an open variable that could be anything. So we assign it to a symbolic value. And you can actually see that in the call data of our paused state. So if you're familiar with how the function dispatching of a smart contract in Solidity works, so you have this call data where the first 4 bytes are basically the name of the function that you want to call. So these first 4 bytes, you can see them. I don't know. Can you see my mouse, by the way? I'm pointing here.
Yeah, we can see it on the selector, right?
On the selector, right. So this is the function selector. It's a 4 bytes cryptic hash. It's just the internal name of the withdraw function, really. And then you can see that there's something else in the call data. And this something else is the symbolic value that we assigned to this WAD variable, to this VAT variable. So you can see, well, this is a Solidity variable. And this here, in the call data, that's a symbolic variable. And we can see it has an integer type. So let's execute over this require statements. And well, let's first try to think what could happen when we execute over this require statement. Well, we don't know what is the balance of the message sender because the storage of the contract is also fully symbolic. And we don't know what is the VAT value. So I'd expect that there are 2 possible code paths, right, that we must consider. One where the require clause evaluates to 2 and one where it evaluates to false. So let's see what happens. And I want that you pay your attention on this call stack and what happens in this bottom left corner of the screen. So going to execute over the statement, and you can see that my control flow branched into 2 different branches. So these are my 2 alternative timelines, my 2 alternative futures. You can see that one of these, the bottom one, branch 3, is an exception. So that is the branch that reverts. And you can see that it's stuck in line 41. And the other branch actually jumped to line 42. So the other branch, the branch 2, is the one that passes the require clause. So I'm going to, when I try to execute this this reverting state, it will just disappear from my call stack. So I'm going to do that, and this just leaves us with the other branch on the call stack. So now we are looking at branch 2. The other branch is just disappeared. And like I said, when we are executing over if statements, we are learning additional information about our execution. And the same is true when we execute over a require clause, right? Now we know that this condition must be satisfied, or otherwise we would not be here in this state. So, and I can inspect all my path conditions, like everything that I have learned about my execution. I can inspect it in this path conditions view here in the left, in the top left corner. So I'm going to expand this, and you can see that we already collected a bunch of knowledge, and most of these is just coming from the types. So I can, for example, I can see, hey, I have this symbolic variable, which is a message sender, and the message sender is of course an address. Internally, it's encoded as an integer. But I know that this integer must be at least 0. There are no negative addresses, right? And then there's another constraint here about the message sender that tells me message sender is at most this cryptic value, and I think this is the max value of a 20 bytes unsigned integer, because addresses, I think, are at most 20 bytes long. So this is just 20 bytes set to all ones. And there are other constraints here that are also coming from the type. So let us see what we know about this vet variable. You can see it here in constraint number 6. They are numbered. I can see, well, this vet variable is also an unsigned integer, so it must be at least 0. And what else do I know? Here's the max value of this vet variable. It's at most, well, 2 to the power of 256 minus 1. And if you look at the bottom, like the last constraint, you can also see this more complex constraint that is telling me that the vet variable is less than or equal to the balance of the message sender. So this is the information that we just learned by executing over the statement. Let me see if I can make this visible. I know it's like the user interface is not optimal at the moment, so you can see that these symbolic expressions that you can see here in the path constraints, they can grow really big, and then they run out of the screen and you need to scroll. So we are working on like giving them a nicer syntax and making them more make them look more like Solidity expressions. But at the moment, that's what we have. But
may I ask a question, please?
Yeah, of course, please.
Okay, so about these path conditions. So these are probably generated by the tool, right? All the path conditions, if I'm right.
Yes, these are collected by our symbolic, like our backbone here, the symbolic execution engine that's running under the hood. That's called KVM. And KVM is really executing over each single, it's working at the bytecode level. So it's executing each bytecode instruction in a symbolic state. And while it does that, it collects all these path conditions.
Okay, pretty nice. So if I'm not using your tool, I suppose I should write it by myself, like all the path conditions is the right way?
Absolutely. That's how, yeah.
Oh my God.
Actually, that's how we invented this tool. Like we had our auditors, well, at one-time verification, we do audits and formal verification, and we had them like collecting all these path constraints manually. So I did this personally with pen and paper, actually. I printed out the source code. Literally, I printed out source code, and I took a pen, and at every possible execution path, I wrote down the possible path conditions that could bring me to this state. And that's what I figured was like a dumb part of auditing. but it's a necessary part because you want to dig into all the possible edge cases. Bugs are often not on the happy path. Bugs are often on the edge cases. So you wanted to just to convince yourself to increase your confidence that your analysis, your security assessment of the token that you are going to evaluate is doing something worth. You need to look into all the path constraints and you need to bookkeep them somewhere. So I did this in pen and paper. I found this annoying as hell. And I think that's how we started inventing this tool. It's like, hey, can we automate this to some degree? Can we not just have a tool record all these path conditions for us and point us, like list out all the possible branches, give us all the path constraints that lead to these states? Yeah, but I think if you're not wanting to use a formal methods tool, if you just want to do manual audits, that's still a good practice to do. It's better to have these path constraints written down somewhere, even on pen and paper, than not doing it at all, or like believing that you can keep them all in your head. So
okay. So it's funny for me because I'm thinking that, for example, for the withdraw function, if you would like to write unit tests, actually you are testing like it's an address, a new int, and things like this that when you are looking at the code, it's not something like logical to test. Like it's of course like this, but I assume this is not like real testing, like testing all the paths. I assume the paths, like I assume these paths are right on normal testing.
yeah, on normal testing, well, there's different techniques how you can make sure that you increase your test coverage, right? So
Yeah, but even with test coverage, I don't test things like the message sender, like on the path conditions here. So I don't test the message sender, it's an address or a event.
yeah, well, your tests are only as good as your specification. The same is true, but the same is true for formal verification and for well, all security assessment techniques, basically. Yeah, but the thing is, well, symbolic or symbolic execution in general can point you to all the edge cases, really. And then when you step through your code, like we do here, we might notice a case that we do not have a test case for, right? So if I'm executing my withdraw function, I know my test suite, and I'm suddenly ending up in a branch, and then I'm like, whoa, I didn't think of this case before. We don't have a test case for that, but we probably should. So actually, it's symbolic execution is also like a good guide when it comes to increasing your test coverage and inventing new test cases.
Okay, thank you.
Here, I think I can also make one additional comment. So the idea is that our symbolic execution engine is not limited to the data types that are used in EVM semantics. So for example, wherever you see that lower than int or equal int, that is the integer sort, whereas the EVM works with int that goes only as big as 32 bytes. So we actually have to constrain these variables to say that, okay, this has to be an EVM word, so we have to limit it to be less than 32 bytes. So yeah, a lot of these constraints are just limiting the range of the variables.
So you've created a tool that it's not only for Solidity, but you like made some settings for Solidity.
So yeah, and this can go very well into a rabbit hole. So the symbolic execution engine that we have is based on this K framework language, in which, in a few words, you can define how a programming language works, and then this K framework is able to generate you a lot of tools for your programming language that you defined. And what we did here is that we defined how EVM semantics works, and the K framework enabled us this symbolic execution. But I'll let Raoul continue from here, I think.
Okay, thank you for explanation.
Yeah, and I have, yeah, you are basically predicting my next slides. So, but let me just wrap up the demo real quick. So we can see the path conditions. See, there's a lot of path conditions that we collected. Let me see what happens if I execute over this function. Seems that it's not branching on this statement, which is kind of expected because, well, there could be an underflow here, but we just checked against this condition. So this underflow is actually not possible. So we don't need to branch in this situation. We can just assume that we are on the happy path. Yeah, other features, well, try it on your own. I just want to give you some idea of how this tool works. But one really essential feature, especially if you are a security-minded person or if you are dealing with low-level code, if you are a gas optimizer, then this debugger also has a mode to work on the bytecode level. So I can actually here open the disassembly view, which loads the bytecode, and you can see in the right column here, you can see the disassembled bytecode. You can see the next operation that I'm going to execute is a caller operation, so I'm executing over that. And here's a stop operation, so we are going to revert now. Yeah. So this assembly view, this is more for the expert users, but internally we find it like super helpful also to understand what is the Solidity compiler doing, what is it like, how does the code look like that the Solidity compiler generates, and it's far from given that the Solidity compiler has no bugs in it, right? So if you really want to secure a protocol and you don't trust that the compiler does everything correctly, then you also want to look at the bytecode, at least in like on the most critical code paths maybe. Okay, but again, go to this try symbolic runtimeverification.com demo, convince yourself, try it out, shoot me your feedback, feature ideas. So I'm going to go back to the presentation. And yeah, you just asked about what is this, like, does symbolic only work for Solidity or does it work for other programming languages? And I didn't expect this question, but you really predicted my slide here. So let's talk a little bit about how symbolic and control, the tool that Andrei will present in a minute, and how they fit into our runtime verification tool suite. So at runtime verification, we have like lots of tools that are for other programming languages, but at the core, they are built around a really elegant and really tiny mathematical logic that is called matching logic. And I think it only has a handful of proof rules. So that's a really tiny mathematical core. And everything else that we build at runtime verification is built around that small mathematical core. So that is basically our trust base. So around this matching logic core, we have this, what we call the K framework. K framework is a programming language for designing and building tools for programming languages. So you can build tools on top of K for Solidity and KVM. But you can also use it to build a semantics for C or for Rust, and kind of develop the same tooling as we've done here with symbolic and control. So symbolic and control are just two specific instances of how you could use the K framework. Okay, I think yeah, I want to give everybody the chance to ask one or two questions. Maybe we have time for that, and then I will hand over to my colleague Andrei, who's talking a little bit about control and takes this entire concept one step further.
Yeah, I have a question. Can you hear me?
Yeah, your microphone quality is not that good, but
Sorry
just shoot
about
me a
it.
question.
Yeah, I saw this cool visual graph in the presentation. Is it available in the demo?
Oh, that's a good question. And the answer is a qualified no. We had to, like last minute, we had to disable it before we released this online demo, just because it was not stable enough. But we are stabilizing it now in the background. So it will land there. It will land in the online demo soon. I cannot say an exact date, but it is definitely still on our roadmap, and it's one of the highest priority items to get this nice visualization graph into the demo, into the tool in general. So also, yeah, speaking of updates, you don't want to, like, when we push out this graph, for example, I will make some noise on Twitter. So yeah, go to our website, try our tool. We also have we are currently hosting a closed beta version that works a little bit differently. That is instead of working on top of Control, it works on top of Foundry. So if you have a Foundry project and want to try a debug on it, you can sign up for a closed beta version at the moment. Yeah, and then follow us on Twitter. Shoot me your ideas, shoot me your feedback, shoot me your questions. And yeah, thanks for having me. I'm going to stop screen sharing so that Andrei can take over.
I've got disconnected. I had one more question, if it's possible.
Yeah,
So,
of course.
okay, so it's just a first question. You said that on that circles diagram, you said that if I'm correct, you are starting from mathematical assumptions, right? So I'm curious that it happened for you, like to have a mathematical wrong assumption about like your core product that happened to go wrong to maybe many layers.
So not on this well, not on this mathematical core, at least, well, not that I'm aware of. I'm also like, this matching logic has been developed like in academia for over 20 years, I think. And there's if you're into mathematics, we have some strong theorems that shows that matching logic is as expressible as calculus of constructive, what's called calculus of constructive constructions, for example. So what's underlying theory improvers such as Koch and Actor. So we have all these strong mathematical theorems connecting it to other mathematical logics. But we had, like sometimes, for example, if you have a programming language semantics, you add new assumptions to your core calculus. You add new axioms, basically. And we had the cases where these axioms were unsound, so they should not have been added to the code base. Luckily, all like these mistakes, they were just like, they did not lead to any missed bugs or so in our analysis, and we were able to identify them. Yeah, but if you are not doing things carefully, and if you're adding axioms to your mathematical core theory, then yeah, you could end up in an inconsistent theory and prove basically anything about your programs, even if that is not true. But unfortunately, it never happened in this. The impact was never that big.
Okay, thank you for.
Can I ask a question?
Yeah, sure.
Yeah, in the demo, it is a number comparison. It is bigger, it is less. But if it is something more complex, not assume, I mean something logarithmic or whatever, it is translated to opcodes, and the opcode it is finally also a branch. I don't know if I did a good
Yeah, you
question.
made this clear. Yeah, so I mean, all these path conditions that you see here, they are coming from the EVM bytecode, right? They are not coming from the Solidity source code level, because that's just how our execution engine works. It works on it works on the bytecode level. So that's why these formulas look so complicated. And to be honest, they don't even come from just the EVM, low-level EVM, but they come from a formal model of the EVM, which we call KEVM. So the logical formulas that you're looking here at, they are K terms or K expressions. And K expressions are really just these matching logic expressions that I talked about earlier, and they can be arbitrarily complex. So as I said, they can be, well, they're at least as expressible as the calculus of constructive constructions. I don't know what the name, but yeah, so these just to make it short, these logical formulas here, they can become really big, they can be complex, they can have logarithms in them. Yeah, basically everything that you wish to express in everything that you wish to express in some mathematical way could end up in these path conditions.
And if in a language there is some random function, the branch was the same.
Well, for EVM, we are lucky and we know that there's no random function that you can implement in EVM, right? It's a deterministic programming language. But well, we also have a semantics, for example, for C, and C is not a deterministic programming languages. There's all kinds of unspecified behavior or underspecified behavior. You can have random functions, but we have a C semantics that's quite complete. And so this approach also works on the C level. Yeah. So we don't have, we don't hit a theoretical boundary yet when it comes to like non-deterministic behaviors as random functions, for example.
Okay, thanks.
Okay, sorry, I'm taking time away here from Andrei, but yeah, please feel free to shoot me your questions offline, or maybe we have some, like if you want to stay longer after the 90 minutes of this conversation, I will hang around a bit to answer all your questions, but I want to give Andrei now the chance to do his part of the presentation. Thanks.
Yeah, thank you. So yeah, I'll share my screen in a second. Okay, can everybody see my screen?
Yes.
Okay, cool. Thank you. So yeah, before I dive into the presentation, I like to talk a bit and say a few words about formal verification. So formal verification, it's not this golden goose of security. So it's not like, hey, I've done formal verification, now my contract is unbreakable and has no security vulnerabilities. That's not the case. Formal verification mainly consists in writing a specification of what your contract should do, and then proving that your contract behaves according to that specification. So of course, your formal verification will only be as good as you write your specifications. And at runtime verification, we use the symbolic execution to prove that a bytecode of a Solidity program behaves according to a specification that is defined starting from the Solidity test that I'll be showing later in the presentation. So with that in mind, I'll be talking about control, which is basically the tool that we've been developing at runtime verification, and we've been using it for engagements for the last year, and it's basically made out of two components. One is the KVM, which Raoul already introduced, and it's this formal semantics of the EVM machine, the EVM opcodes, and how they work. And this KVM implementation being implemented in K, this means that we can use the symbolic execution engine. Now, this semantics of EVM, this KVM, can also be used as a node. So we could modify it to basically connect it to a node like Geth, for example. It also runs on all the tests that the Ethereum Foundation provides, and it passes them. And yeah, it has been developed from 2016, so it has some time now. And yeah, we have this EVM semantics, and then on the other way around, we have the Foundry framework, which gained a lot of traction in the last year, and it's a popular framework for Solidity developers that it's a bit similar to how Hard Hat and before that the Ganache and Truffle worked. One additional upgrade is that developers can now write their unit tests in Solidity directly, so they don't need to use TypeScript or JavaScript. And one additional step is that these unit tests can now be fuzzed. And so I'll talk a bit about the project structure and then show some examples of both Foundry and Control. So yeah, the project structure is similar because when we developed Control, we wanted developers to have a better experience. So to avoid creating multiple projects of basically the same source code and avoid duplication. And so the project structure is I think it's a bit intuitive. So it has this source folder where developers write their smart contracts, and then it has the test folder where the tests are written. The contracts containing the tests are written. And then you have another important folder is the lib folder, which contains additional libraries required. And there are two highlighted libraries that I'll talk about shortly. And then there's the out folder in which the Solidity compiler puts all the artifacts of the contracts, like the ABI and the abstract syntax tree and all of that. The idea is that we use these artifacts, these JSON files, to create the specifications for the contracts that users write. But yeah, the idea is that the test in Solidity has looks like this, and this is again the wrapped ether contract that Raoul was presenting in the symbolic demo. But basically how it works is that we define a new contract that basically is a wrapper over the initial contract. So we have an address or a reference to the initial contract that we want to test. And all of these test frameworks have this setup function, which is basically the first step before you want to execute a test. you run the setup function, and then you make some kind of snapshot. And then on top of that snapshot, you can execute each test that you have in your test contract. So in this example, we would initialize the contract, and then we would generate 2 addresses. And then whenever we want to execute a further test, these Alice and Bob and the address of the asset wrapped ether contract will be the ones generated in the setup function. Oh yeah, the libraries. I almost forgot that. So I told that there are 2 additional libraries, the Forge standard library and the control cheat code library. The idea is that in order to manipulate the EVM, the Solidity language, it's a bit restricted. So you can't set the message sender, or you can't set how much ether does an account have initially. So for these scenarios, Foundry developed, or before that HEVM, I think, they developed these cheat codes, which are basically a contract of functions that don't have any implementation. These are abstract functions. But when you make a call to a certain address with a specific call data, which is the hash function of this cheat code, then the EVM implementation of this framework will have a specific handler for that function. So in this test approve Alice to Bob example, we see this vm.prank of Alice. And what's happening here is that we're mentioning to the virtual machine that's running underneath that we want the message sender to be set to this Alice specific address that's generated in the setup function. So yeah, there are a lot of cheat codes that are defined. They are public online. Control also supports, I think, most of them, or at least the most common ones that Foundry uses are used as well as Control. And on top of that, Control also have some specific cheat codes for symbolic execution. Okay. So I think I covered this slide. I think I can jump to the terminal to see if I can run some tests actually. Okay, not this one. Let's use the Visual Studio Code. So we have this Securium control repository that I'll share at the end of the talk. Let me actually turn on the lights. So I think let me increase the font as well. So in the wrapped ether, I think I'll focus on this test deposit function for now. Or actually, I think I'll use this test approve Alice to Bob because it was also in the slide. So yeah, the idea is that you can basically Forge build everything to compile the source files, and cool. Then you can run a specific test, which is, I'll use this one, and I can do forge test dash match a specific test, and I can paste the test that I'm trying to execute. And yeah, I'll run it, and I can see that the test passes. And additionally, I can see that it had 256 runs. Now, what does this mean is that the fuzz framework underneath Foundry was able to generate 256 different inputs for this amount variable, which is an argument to the test. Now, if you want to write plain unit tests, then then you can just avoid having an argument to the function, and now the function is just a plain unit test, and you can define the U/56 amount here to have a certain value. Yeah, regardless of that. But yeah, this fuzzing also has some limitations. And I'll use another example here. This is an example that we have in the documentation as well. So I don't know, for example, this is a very basic contract that has only a uint field and it has an error defined and two functions implemented. And the set number function would basically take a number and the Boolean flag for some reason, and will assign the number. But if that number has a special value, which I'll call coffee, and the Boolean argument has a certain condition, then I want to revert. So this is used to show that basically how complexity affects fuzzing. And the idea is that if now I want to run these forge test match test, and I'll jump ahead. So in a similar way, I have a test contract defined for this, and I have a test set number, which basically takes two arguments that have to be fuzzed, and then I can pass them to the contract function, and then they'll be asserted. And so I can just do match test of test set number, and it tells me that the test has passed. It again tries to run it for 256 times, and then it doesn't find any issue with the function that's happening here. Now I can increase the fuzz test. So let's put a flag saying that I want to run this for 1,000 times. And again, it tells me that it passes. Eventually, if I increase these around 10,000 times, at some point, it perhaps will find the issue. So, okay, now it found the path condition or the random value that's supposed to get on this revert branch. But the idea is that the more complex your function or your logic is, the harder it is for a fuzzer to identify that scenario. So yeah, that's what I wanted to show on Foundry. Again, if there are questions at any point, please interrupt me or put them in the channel. Okay. So yeah, now this was Foundry. The idea with control is that as Raoul talked about symbolic execution, we can take now this Foundry framework that is here, and we can take the symbolic execution engine, and we can combine them together. And what we end up getting is that we can get symbolic exploration and we can get symbolic testing, which I'll explain again the difference between the two. So what Raoul demo in the contract, I think he debugged the withdraw function, which basically was a function of a contract, so it was not a test. In that case, it was the symbolic exploration happening, where over the arguments of a function, basically those arguments became symbolic, and then we started executing the contract code. Now, the difference between symbolically executing a function and symbolically executing a test from these frameworks is that a test also has a few additional criterias. So at the end, we want the function execution to not revert, and we don't want any assertions to happen. We don't want any assertions to fail. And there are these criterias that basically define how a test should pass. And I think the difference here is that if you prepend the test, prove, or check words before the name of the function, then is going to be considered a test. And then if your function doesn't have that, then it's going to be considered a symbolic exploration case. And yeah, we have some additional special cases like constructors and setups, but I won't go into that. So in program verification and in formal methods, there's this concept of Hoare triples. And we try to adapt that. And with this way of writing tests, I think we can apply them in Solidity testing as well. So basically, a Hoare triple, it's something that says that for any kind of for any variable, I have a set of preconditions, I have a code, and I have a postcondition. And what this means is that for any possible input, I have some preconditions that hold at the beginning of the execution of the code. And then I have to execute the code. And after that, the postconditions should hold. And so we can take this concept and apply it into this structure of solidity tests. And basically, we can use the assume cheat code or the assume function to set a preconditions for a test. And then we can have the code to be executed, and then we can assert post conditions. Now, vm.assume is basically another special cheat code used by Foundry and Control. It's basically used to filter variables, or you can put a boolean in this assumption, like I want this address field, whatever, to be different than a specific address, and then what happens underneath is that this becomes a path condition. Was it a question?
Huh?
The guy that got him straight, just picture of the password.
Which guy?
You're not aware, babe, about
No,
what's
I'm in a meeting. Yes.
Go ahead, Andrei.
Yeah, sure.
Someone unmuted.
Okay, sure. So yeah, I was saying about these precondition and post conditions and how they can be applied in symbolic test in solidity testing. And I think the idea here is that there's the concept of the weakest precondition and the strongest post condition. So in general, preconditions, the idea is to have them as general as possible. So start from a state where you only know the minimum things that you need for the execution to happen, and then the post condition needs to be stronger so that you can have a higher confidence in your correctness. And there's also something that's in between the preconditions and the post conditions, which is called invariance, and I'll touch those shortly. So yeah, now about control. I told earlier that it's similar to Foundry, and then it's basically this is a list of the initial commands that you can use. You have the control build, which basically runs the same as forge build, and it compiles the solidity code, and then it generates the specifications for each contract and each test using this KVM framework. And then you have control proof, which can take an argument of the test you want to test. And what proof will happen is that when you run control proof, you will actually execute the specification with symbolic execution. And I think I can go back to the terminal here. So yeah, in the interest of time, I ran some proofs before the meeting just to save time. So the first command that I can show you is the control list, which basically lists all the proofs that have been executed in your project. So yeah, in this example, I wanted to run this test deposit function, and I also wanted to run this test set number that I've been showing earlier with the coffee break. And so you can see that I have a proof for the setup function of that contract test, and I also have a setup function for a setup function for the wrapped ether contract. And then I have two other proofs for the test that I wanted to run. And surprisingly, in the interest of the meeting, both tests have the proof status of failed, but the setup functions passed correctly. So just to show how the process would do, I could do control proof -- match test, and you can either put the full name of the function, or you can do partial matching. And here I'll just do partial matching. So I think I can do this test set number. And now it will take some time to spin up the internal servers and everything that's needed, but should take a few, perhaps 30 seconds or not, or less. And the idea is that while this is running, I was sorry. I was saying that what happens here is that underneath control is able to run this KCFG, or basically control flow graph of how the execution develops with this symbolic execution engine. And it will generate nodes in this control flow graph, and each node is compared with a target node, which we define of how the post state should look like. Okay, so what happens here is that we see some not so easy to read messages, and these are actually the failure reasons or the path constraints that led us to the failure. But the idea is that we can see here the path condition of which our execution failed. And basically what's saying here is that whenever x is equal to a certain number, because here I have a double negation, but and whenever the in luck symbolic variable is different than 0, then I'll lead to a node that fails. And in addition to this, I get a model which basically says instantiates all the symbolic variables that we have in the test. They get initialized, instantiated with a concrete value. And I suppose this number here is the hex coffee number that I was showing in the test. And so one additional step that I can do here is that I can do control show on the test set number. And 1 second. It will display this control flow graph in the terminal, and I'll try to go through it. And yeah, the idea is that, as I said, we have these nodes of the KCFG which represent various snapshots that were taken during the execution of the test. So this number of steps is representing that, okay, before the two nodes happened, there were 1,256 operations that happened. And I won't go, you can ignore this code for now. I know it's not readable, but what's interesting is that at some point I see that there is a split on a jump I up code. And then I see a branch happening, and I see this constraint saying that, okay, whenever x is not equal to this number, the execution continues, and this is added to the path constraints that Raoul was showing earlier. And so if I go down this path, I see that at some point I end up with an EVMC success status code, and I see that the terminal node is basically subsumed into the target that we were trying to achieve. And then we have the second branch when x is equal to the number, and then it will do some processing, and again it will reach another branching point, because what happens here is that I have an end in the if condition. And so at the bytecode level, somehow this gets split into two if conditions, one after the other. So then here again I have the second branch constraint based on the Boolean argument that I had. And so on one path, again, I see the EVMC success, and that it gets subsumed into the target node. And then again, on the last branch, I see that I have the EVMC revert status code, meaning that the execution failed here. And now, if this doesn't have, if this is not, if you still want more information about this, then you could use the control view KCFG option, which again will take the test. And this would display CLI implementation of KCFG viewer. So here now you can actually explore or the control flow graph. And I know I can maybe put this down. So basically now you can browse the control flow graph, and then at each node you can basically inspect the state of the EVM at that point. And here on the right hand side, I would have the options that I have available. I have the some basic information like the test name, the status of the proof, and the time it took. So for this, it took a bit over 2 minutes. And then I have 3 more cells. So I have the one on the bottom right, which this is the source code, and basically using source maps, it theoretically could point wherever you are in the node to the specific function that you're in. But this is not always working correctly because the Solidity compiler does a lot of optimizations, so usually the source maps are not very accurate. So for now, I'll just disable it. And then I have 2 more items. One is the one showing the path constraints that I have available at this point. And then the other one is for the configuration. And this is basically a snapshot of how the EVM machine, the EVM state is at this point in time. I see that I have, for example, I have the program bytecode here that's loaded into the EVM. I have all the jump destinations that are available. I have the address that's currently loaded, and I have the call value and the local memory. And so everything is defined here to be available. Now, again, this is not, I know it's not very easy to read, so yeah. Okay. Now, I'll also run the second the test deposit proof. And while this is running, I think I can no, I think I'll continue a bit with the test. Sorry. So yeah, again, it takes some time to basically read the proof information and use the, if it identifies a failure, and then it basically calls to SMT solver like Z3 to basically generate input for those failing constraints. And it basically takes time to generate that model at the end with the concrete values. Or perhaps I forgot to run this proof entirely and it runs for the first time now, which is also very possible output, and seems to be the case. No, okay. So yeah, in this test, I think I can put it side to side. Oof. I'm not good with these. Okay. So in the wrapped ether contract here, I think I can close this. We have this test deposit function, which basically takes an address as an argument, and then we have an auxiliary function called not built-in address, and this is something that we use to trim branches that we don't necessarily we are not necessarily interested in, because when you have a symbolic address, at some point it's going to assume that it's going to compare that address with all the addresses that you have available in the state. So to avoid re-executing or executing multiple times the same code paths but with a different address constraint, we just assume that the symbolic variable is different than the subset of addresses. And then we set the message sender to be equal to this symbolic address, and then we want to deposit a value that's the message value. And yeah, running this function, you can see on the right hand side that the proof is failing. At some point, we have this path condition saying that the proof is failing when the call value is greater than 0. And I can go off, not in this one. So yeah, we can see that at some point it's doing a check balance or underflow on the from address, and then there's a branching on the call value of the function of the payload that we're making. And so if at any node I look into the, let me close again these ones. If at any point I go in the account state, this is the account state, and this is how accounts are represented. We have the address, the balance, the code, and so on. So at some point, we're going to see this account that's here with the symbolic from address, and we can see that the balance is 0. And why the test is failing is that whenever we're making this, deposit function, if the message value is higher than 0, then the test would fail because we don't have the balance to do it. So what we can do here is that we can do vm.deal to the from address. We could deal, let's say, 10 ether. But I'll ask, this is like an open question, what do you think it will happen in this case? Say that I recompile the proof and then I run again. Any suggestions or any idea? Okay, then I guess we can do control build, and we can also do control build dash dash recompile, and then we can do match test deposit dash dash rainit. And what basically here is that I've changed the Solidity code, please recompile everything, and then I'm proving with the dash dash reinit, meaning that I want to start a new proof instead of continuing the initial one. But while this is running, I think I'll go back to the slides. As I said, I'll be all over the place. So yeah, the idea is with symbolic execution is that it gets a bit complicated when loops are involved. Because the idea is that loops are kind of like treated like black boxes. You don't know at which point in loop you are. You don't know if you're at the start of the loop, and you don't really know if you are like at the end of the loop. And so it's a bit complicated when you want to do symbolic execution on loops. Now, I think there are two main ways to handle this. And also, as a side note, I can tell you that here this function has more than one loop. So I don't know if you can see the second one, but we're also discussing about that one. Yeah, so the idea is that there are two ways in which symbolic execution can handle loops. The first of it is that you can do bounding. So most symbolic execution engines would like identify a loop and then do it for a number of iterations, like 3 or 4 or 10 times, and then it will automatically jump out of the execution. And this is possible because in the bytecode you can identify where a loop head is, both by how the loop head looks like and both of like the program counter that gets repeated over time. And so you can basically bound the loop by executing it a finite amount of times, but then if you run a loop for 10 times, you're still not certain that the problem won't be at the 11th time of executing the loop. So the other approach is with something that's called an invariant. And basically, invariants are these properties that have to be valid at any point in the execution of time. And so this function, I haven't tried to execute it, and I'll show some overly simplified invariants just to develop your intuition and show you how these invariants are supposed to look like. But in reality, whenever we have to work with invariants, they are very brittle, and whatever change we make to the source code, we have to modify the invariants and update them again. So this is a Solidity function that I wrote that basically takes an array and it returns the minimal value of the array. And so if you would want to write invariants for these functions, basically when you have invariants, you need to show that the code you want to execute has a termination, and you also want to show the partial correctness of the code. Basically, again, you have to specify what the function should do, and then you have to prove it. So to show the termination of the code, I basically drafted an invariant here that says that at any point of the execution of the loop, of the for loop, the I iterator has to be between 0 and the length of the array that we have. So this will be valid before the loop, during the loop, and even after the loop. And so the second invariant that we need to show the partial correctness of the code, we have the second one here that basically says we take a j, another iterator, and which is of type int, and for all values of j that are between 0 and the iterator I, well, I need to know that the mean variable that we're having defined here is less than equal to a of j. So this means that, again, at any point in the loop, the mean variable will have the lowest element that we can find in an array from the start to the point we're currently at. So yeah, this is basically how you can define, or what's the intuition behind invariants. And yeah, using these and using the Horde triples, basically you can do program verification in mostly any kind of language, not only EVM. And yeah, I said earlier that there are two loops here. One is visible, but one is kind of hidden. And the other one that used to make us trouble is the use of the dynamic types as arguments. So a dynamic type doesn't have a fixed number of elements. You could basically, it's not known at compile time. So when you're compiling a function like this, the Solidity compiler will actually generate a loop that copies values from the call data to the local memory and the other way around. So we also needed to figure out a way of how we can handle these, because there are other symbolic execution tools out there. We're not the only one, but most of them will, or at least some of them will fail when you want to run it on a function that has dynamic types. And so one way we handle this is that we use the same concepts, but we choose to bound the dynamic types that we're having. So saying that we have a function that has a uint256 and then has a dynamic type of an array, a dynamic type of array, and the array holds bytes elements, which again are another dynamic type. So it's basically an array of arrays. In situations like this, we want to bound the length of an array and the length of an element inside the array. So we use this using a concept called natspec comments. And basically the compiler allows you to use special tags in the comments, and then you can see in the compile JSON, you can see that you can read those values, and that's how we extract this from the Solidity source code. And the idea is that we can basically use a certain tag like control array length equals, and says that, okay, I want the data to have 3 elements, and I can also say control byte length equals to data, which means that um, each byte's element inside the data byte array, I want it to have 200 bytes. And so we can restrict the length of the elements and the length of the array, but the value can be anything in that boundaries, basically. And yeah, I think this is what I had prepared for today. I also think that maybe it was a bit too much. I can go again into the execution of the code, and I can see that the path condition, the proof that we wanted to modify, failed again. And basically because the call value, now the branching is not over 0, but it's about that 10 ether that I used as the initial balance. So the call value is now what happens if the call value that I want to send is 10 ether plus 1, the initial unit that we have. So going back to the code, and I promise I'll finish with this. How you would work around this, you can say that, okay, I want to deal to from whatever the message dot value is that we're trying to send. And so at this point, whenever it goes to that comparison between the call value and the balance of the from address, is going to be the same value, so it won't be a branching. So yeah. Any questions?
Yeah. So, Andrei, about the invariance, you didn't show in the example the invariance that you showed in the slide. So do you have some assume statements, or how do you?
Okay, so this is not code that actually runs. I wish, and I think everyone wish, that we can write invariants this as easy and as readable as these ones. But in reality, EVM invariants are way harder to write, because you basically have to reason about the entire configuration that I showed in that terminal. So you have to reason about gas, you have to reason about how local memory works and all the program counters that are used. And so you can get to a point where you have an invariant that does the job, but then you want to modify something, like even the tiniest bit of change you do in the Solidity code, it will generate a different bytecode, and then the invariant won't hold anymore because the program counters have changed, for example. So yeah, I don't think I have an example of an invariant.
I think we have 2 blog posts in the making that will be pushed out pretty soon that contains a full walkthrough of how you would specify an invariant. Like how would you even come up with an invariant, like at the Solidity level, at the natural language level, then at the Solidity level, translate it to the EVM level, and then actually how to apply it in your proof. That's a bit of a tedious process, but it's the only way we have if we don't want to fall back to cutting off reachable states by using loop unrolling and bounding. Yeah, just stay tuned for these blog posts. They contain a full walkthrough of this.
Got it. Thanks.
Yeah, also all the materials that I've shown previously, I think I can also share the slides here. we have the security control repository where we have these proof examples. Then you can try it. Then we have an entry blog on control. We have the control documentation and the open source implementation of our tools that we're using, and also the link to the symbolic. And then we also have a pretty active community on Discord with this QR code. So you can join our Discord, then you can always post any kind of questions that you have on either symbolic execution or developing, or how we how to use control, basically.
Great. If you the slides are shareable and they're public, so you can just drop the link into the comments, into the
Yeah,
chat,
sure.
and I'll take it and put it on the meetup page.
Sure.
Cool.
Let me see how to
Until
share it.
then. So, any other questions?
I do have a question. Like, so at this point, after this presentation, maybe I will jump to use. I mean, for me, as you explained that formal verification is actually a better. It's better than fast testing. Like, I would replace every fast testing, but I think it's not actually the
So
greatest
It's
idea.
definitely not better in the sense that you should give up all your fuzz tests.
yeah,
You should definitely do both. Like, use fuzzing first, because it's also way faster. And you can write like 1,000 tests easily for a fuzzer. And then once you have these fuzz tests passing, you can take the same tests and throw them into control. I mean, they use the same format. So yeah, but ultimately, I think you should be doing both. Like, use a fuzzing first, and when the fuzzer does not return any more counterexample, use control on top of it, really to get the confidence that you explored every single edge case.
So I also would like to know that where do you feel like it's more important to do formal verification? Like, on, like, I'm imagining on protocols or things that have huge complexity, maybe. So I'm assuming not all the development should use formal verification. I mean, I understand this is the the pure way to go, but I don't think for like small projects and things like this there is make any sense to use.
so I think the main resource here that you have to take in consideration is time. Basically, how much time you have to devote to do the symbolic execution, because we're trying to make it as easy to use as possible by, as I was showing here. Basically reusing the same test that you use for fuzzing, you can use symbolic execution over them. But at some point, even if you run those tests with symbolic execution, you can go into these states or these branches that you have to spend time to basically understand what's happening there, and if it's to understand if it's a valid branch or if it's just some um, again some branch that you're really not interested in. And so you have to spend a bit more time to do this. And it's also the fact that as I was going towards the invariance topics, uh, it takes uh, it takes some time to execute something symbolically. So the examples that we have here take around 2 to 5 minutes, but if you run some more complex code, you can get towards a few hours. And I remember a few, like last year or so, we worked a lot on performance and we were able to achieve these times that are you seeing now. But we used to have proofs that would take 3 or 4 hours in like the best scenario. So yeah, you don't. This was not a presentation in which we're trying to convince you to drop unit and fuzz testing. So those are great ways to test your project, and you shouldn't drop them. This was just something that, okay, you have a test suite with which with which you're happy, but you still want a higher level of confidence, then you can use something like control on perhaps on your CI to run before the release, for example. And yeah, also I was talking about invariants. So because of the fact they are so brittle, you can't even, it doesn't really make sense to write an invariant early on in development because it will change a lot through times. So yeah, I don't know, Raoul, do you have something to add on this?
Yeah, so obviously it makes sense to start formal verification with the most critical code paths in your code base, like the one that are transferring assets, obviously a good target, and then work from there. I mean, if you're a security-minded protocol, you go through different security audits maybe, and that's also a good chance to talk to the reviewer team and ask them what they think are the most critical code paths, because they may come up with like new scenarios that you didn't know about, and so they can inform this process. Hey, what should be formally verified next in our process? Yeah, always good. Like start with the functions that transfer assets, and then ask your development team, ask the auditing teams that are looking into the code base what else should be covered, what is a risky function, and start from there. Yeah.
Okay, thank you for explanation.
Oh, great. So if there are no other questions, we are 1 hour and 45 minutes into the presentation. So last call. Okay, then. So thanks a lot, guys. So great presentation, and personally waiting for the tools. I'm really looking forward to try the symbolic debugger. And let's keep in touch. And when you have some news, just drop in some messages. So let's talk again, and hope you have a nice release of the tool. And
Thank you, and thanks for having us. It was a pleasure. Looking forward to the recording.
Sure.
Yes,
Sure.
thank you.
Okay. So thanks everyone. See you around.
Bye now.
Thank you.
Yeah.
Thank you, everyone.